Good evening all. This is the last slide, my video of the module 3B related to downlink transport channel processing. In this video, I am going to talk downlink reference channels and HARQ on downlink. Downlink reference signals. Downlink reference signal consists of known different symbols that are extended for downlink channel estimations at the UE user interface needed to perform coherent demodulations. To facilitate that estimation process, scattered reference signals are inserted in the source grid as predetermined intervals. The time and frequency intervals are mainly determined by the characteristics of the channels and should make a trade-off between the estimation accuracy and overhead. There are three different types of downlink reference signals. One is self-phase-specific reference signals, MBS FN reference signals, and vision phase-specific reference signals. The reference sequence is generated from the pseudo-random sequence with different initialization for different types of reference signals. There is one reference signal transmitted per downlink antenna port. For MBS FN reference signals, identical sequence transmitted from cell involved in MBS FN transmission, while cell-specific third types of downlink reference signals. Sequences are used for other types of reference signals. In this subsection, we describe how the various reference signals are mapped onto the physical layer resource element. Cell-specific reference signal. Cell-specific reference signals, we have listed out the first slide, are transmitted in the all downlink subframes in a cell supporting non-MBS FN transmission. In the subframe listed for the transmission via MBS FN, only the first two OFDM symbols can be used for cell-specific reference symbols. Cell-specific reference signals are definitely separated for the antenna port 0, 1, 2, 3, 4. We are having 4 antennas at the transmission. That way we are giving it 0, 1, 2, 3 as notation. It is given in figure. Therefore, in LTE, maximum 4 antennas can be used while transmitting the cell-specific reference signal. The cell-specific reference signal are defined only for the normal subcarrier spacing AF equal to 15 kHz. That is the spacing of the guard as a guard. The time domain of the antenna port 01, the reference symbols are inserted within the first and the third last OFDM symbols in the each slot, which is the first and fifth OFDM symbols for the normal CP, and the first and fourth OFDM symbols for the standard CP for port 2 and 3. The reference symbols are only inserted in the second OFDM signal, so internal port 1 have twice as many reference symbols as antenna port 2 and 3. This is to reduce the reference signal overhead but also cause an imbalance. Cell-specific reference signals, you can see it how exactly it is being listed out. How is the frequency, antennas port, antenna 0, antenna 1, antenna 2 and antenna 3. This is the difference we are using it. MBS EN reference signals. MBS FN reference signals are only transmitted in subframe allocated to MBS FN transmission, which only defined for a standard CP and transmit over antenna port 4. In time domain, the win number slot, the reference symbols are inserted in the third OFDM symbols AI 15 kHz and the second OFDM symbol at that is 7 kHz. For odd number slot, the reference symbols are inserted in the first and fifth OFDM symbols and AF delta AF 15 kHz and in the first and third OFDM AF 7.5 kHz. MBS reference signal continuation. In the frequency domain, the reference symbols are transmitted every 2 subcarriers for F equal to 15 kHz and every 4 carriers that is equal to 7.5 kHz. In the Dual-state OFDM symbol, the reference symbols are transmitted from the second and third subcarriers. It is defined like this, otherwise they start from the first subcarrier. Based upon these rules, all examples of resource mapping MBS FN reference signal are shown in figure with the extended CP, that is guard, and that is AF equal to 15 kHz. Note the density of the MBS FN reference signals in the frequency domain is 3 times higher than the cell-specific reference signal. This is because of S1 transmission includes the highly frequency selective channel, so it requires a high density of reference signals in the frequency domain. Synchronization signals. The downlink synchronized signals are sent to facilitate the cell search procedure, during which process time and frequency synchronization between user interface and eNode B base station is achieved and the cell ID is obtained. There are total 504 unique physical layer cell ID which are grouped into 168 physical layer cell ID group, and the physical layer cell ID is group uniquely defined as the down, how it is been defined, where NID equal to 01 to 167 represent the physical layer cell ID and NH equal to 102 represent the physical layer ID within the cell ID group. Each cell is 25 signed the unique physical layer ID, and synchronization signals are classified as primary synchronization signals and the secondary synchronization signal. Primary synchronization signal identifies symbol timing and cell ID index N, while secondary synchronization signals are used to detecting the cell ID group index and frame timing. Synchronization signal continuation. Synchronized signals are designed to such a way to make a cell search procedure fast and low complexity, and that is that to be frequency one frequency division Z of Q sequence. Z of Q SC sequence possesses a constant amplitude 0 autocorrelation property, which means low peak to average power ratio. This is proper desirable for synchronization signals to improve the coverage, and which is an important design objective. There are 3 different loop sequence indicators corresponding to cell indicates equal to 0, 1, 2, which make the primary synchronization signal of different cell IDs orthogonal of each other. The sequence used, the secondary synchronization signal is interleaved concatenation of the 2 length 31 binary sequence. The 2 base sequences are cyclic shift of the M sequence with the shifts specified by the cell ID group, which then is coupled with the sampling sequence specify the value of NH. Therefore, the secondary synchronized signal can only be detected after detecting primary synchronized signal. The use of 2 length 31 sequences make it feasible to detect the 168 cell ID group. MIMO in diversity and spatial multiplexing, you can see here how exactly. One radio frame, it is 0 to 19. That is there, where already we discussed in the TDD time frame 1. A frame structure type 1 already defined your OFDM symbols, which is having one slot which is 0.5 millihertz, and that to be one radio frame equal to almost 10 millisecond, and the frame structure type 1 and frame structure type 2. Same 0, 1 you have to see in the SP here, and there in between, that is how it is being inserted between 0 and 2 it is CP is inserted. That is the things, and same way 11, 12 it is inserted. This is frame structure type 2 is using for MIMO in diversity spatial multiplexing for the for this one subframe to others by using multiple input multiple output diversity technique. HARQ in the downlink, that is in wireless network, due to the effect of channel fading and interference by neighboring channels, they nearly impossible to guarantee error-free transmission no matter how robust the channel coding. To come over this, coding rate decreases and transmission becomes more robust, but at the same time power efficiency is lost and the significant amount of power is used to transmit a few bits of information, and the elegant approach of solve this problem is called HARQ protocol, which is combined FEC and retransmission within a single framework. At the receiver, turbo decoding is first applied on the received code block. If this is retransmission, which is indicated in the DCI, the code block will be combined with the previously received version for decoding. If there is no EIDOI detected in the output of the decoder, 111 acknowledged signals is fed back to transmitter through the POCH physical channels and decoded block to pass to the upper layer. Otherwise, 10 NAK signals are fed back and receive code block and they store in the buffer for subsequent combining. The coding and modulation of HARQ acknowledge information carried in the uplink for the downlink HRQ process discussed. Acknowledge NAK feedback is treated as later mode. HRQ downlink at the transmitter. You can see down the same turbo encoded data is transmitted with the different puncturing, and so each of these three transmitters has one different redundancy version. The each is self-decodable. Puncturing is performed during the rate matching process shown in the figure. The rate matchers, i.e., they produce 4 different redundancy versions of the original coded block. HARQ transmitters are indexed with the preventive version reads, which indicates whether the new transmissions RV IDEX equal to 0 or the RV IDEX retransmission of the 1, 2, 3. For example, 10 millisecond frame with the 8 HRQ process is clearly every frame is 10 millisecond. For this, whether FDD here, so or FDD, but this is to be defined. HRQ downlink, it takes a certain amount of the time of HRQ acknowledge NAK to be received for the system rate to transmit. This is the time interval between two successive HRQ transmitters, which is typically and millisecond LTE. During 8 milliseconds, the transmit block can either be transmitted if received with error or be discarded from the transmit buffer. This implies a certain amount of insufficient transmission since the transmitter has to wait for 8 milliseconds before it takes any action. Definitely. In order to mitigate this issue, 29N channel stop wait protocol is used for the downlink HCARO operation. An N channel stop and wait protocol consists of N parallel HRQ processor. When one or more processors are busy waiting HCAR acknowledge HRQ, the process and that are free can be used for transmit other transmit block. And that is the end of this particular my video. Thank you very much.